Good evening, and my name is Mrs. Jane Owen, and I teach from Penn Gleis School in Aberystwyth. And I join my colleague James Ridd from Cynfig Comprehensive School in Bridgend to deliver these sessions, four of them in total for Year 10, starting with circuit electricity, which was number one, generation of electricity, done by James for number two. I'll be doing this third one for domestic electricity, and finally James will finish off with ways for the fourth session, and then we'll get together and we'll run through some exam time type like questions. Okay, so moving on to domestic electricity. We will be looking at the units of electricity, the equations of electricity. Um, uh, we'll be looking at AC and DC currents, fuses and circuit breakers, looking at the ring main, and then looking at kind of like micro generation of the home, and looking at solar panels and wind turbines, and tying all of that together with a couple of questions using, say, payback time and how long it takes to pay back the cost of installation of appliances. So if we go up and start at the beginning, our domestic electricity, we use two units which are slightly different to what we've been using in circuit electricity. So power is measured in terms of kilowatts as opposed to just watts. Yes, you know that there are 1000 watts in a kilowatt. And when you're talking in terms of domestic electricity, we're using quite a lot of power. So instead of saying 3000 watts, we shorten it to say 3 kilowatt kettle. The other unit that we use in domestic electricity is for energy. It is for a kilowatt hour. Now, normally energy is in joules, and that's what we would use in year 11. But again, because the amount of joules would be so high, you're talking, 3,600,000 for say 1 kilowatt hour, then it's just ridiculous in terms of talking such big numbers. And that's why we tend to use kilowatt and hour, and kilowatts times by the time in hours gives us the energy. And 1 kilowatt hour gives us 1 unit of electricity. So if we have this washing machine here that we can see, and let's just say that the washing machine has got a power of, say, 2 kilowatts, and we're going to use it, say, 5 times in a week, and do our washing for the family. So 5 times, and each one of the cycles is 1 hour. Then we can get from this information the total cost by using these top two equations. So the units used, that is the kilowatt hour, is given by the amount of power in kilowatts times by the time in hours. So 2 kilowatts times by, say, 5 hours tells us that we are using 10 units or 10 kilowatt hours of electricity. And that actual is, in fact, is the amount of energy used, 10 kilowatt hours. That's what we say, 10 units. Now, if I gave you that the cost is 33p per unit, let's say, then the cost per unit would be 33p, and then times that by the number of units used, which would be the same as what you've just calculated, and then the cost then would be 10 times 33, which would be 330 pence, which then, if you convert it into pounds, £3.30. Just a little bit of warning with WJC, they don't like you writing things in pound and pence. So just if it's going to be 330p, then it's in, because it's given to you cost per unit in pence, then you write it in pence. And then if you want to put it into pounds, divide it by 100 and put it into pounds, but don't put the pound sign and the pence sign down with it. Okay, so here we can see one of the typical labels that would be put onto the washing machine. And da, da, da. And here we're being told that the energy efficiency is a B rating, not the highest, which would be A. And in fact, nowadays they are making appliances which have got further categories of A plus, A plus plus, and even A triple plus. But this energy consumption here, they've given us a kilowatt hour per cycle. They've told us that it's 1.75 kilowatt hour used for every cycle. So they have given us the number of units used per cycle. So whereas before I just gave you a general example of how to use the equations, if you're taking the information from this, then it gives us 1.75 units. So actually we don't have to kind of like work out the number of hours or the number of kilowatts. They've given it to us as it is. So if we know what the cost is, for each unit, say 33p per unit, then all we've got to do is times the two to get the total cost. Okay, but you'll notice that this, and I'll let you do that. Okay, and you'll notice that the washing performance is an A rated and the spin drying performance is a B rating, but it's given a B overall. Probably the average between those is probably a high B as opposed to a low A. But that's the sort of information that you would be expected to try and lift from an energy label for the devices in the home. Now, moving on and looking, so we've looked at units and we've looked at using some of the equations. Now, you do need to know what the difference is between what we call AC current and DC current. Now, we use in domestic electricity AC current, alternating current. Now, alternating current is a current that goes basically one way around the circuit, and then half a cycle later, it goes in the opposite direction. So it provides a current at say a frequency of 50 hertz. In fact, with mains electricity, we use 230 volts AC, and we say 50 hertz, and so that means it's going backwards and forwards 50 times in 1 second. So if we have, for example, a 3 volts AC, 1, 2, 3 volt AC, then the current trace, if you like, or here is a voltage trace, so it'll go up to say 3 volts and then down to -3 volts and like that. And then you trace it back exactly the same and like that. Okay, so this is -1, -2, -3. So what you're finding is that the voltage for an alternating current can range anywhere. If it was set at plus or minus, say, 3 volts, it can be any value between a maximum of 3 volts and a minimum of -3 volts. It could be any value between those values. It doesn't necessarily have to be naught, but at one stage in the cycle, it could be naught, it could be 1, it could be 2. There'll be any value. And this enables us, if you have done generation of electricity, by using alternating current in our homes, we are able to transform it. And that is why we have alternating current in the national grid, because we've got transformers at the beginning, we've got transformers at the end, a step up at the beginning, a step down at the end, so that we can actually change the voltage by using a transformer. But can't do that with a direct current. Now, direct current has only got one value only. So if I have that in a different color, do I do that? Okay, yes. Let's go on to, okay, I'll just do it as a dotted line. If it's a direct current, and I'll label that up DC, and I'll label this up AC. Direct current means there's only one value that the current can be. One value only, and the current is going in one direction around the circuit, whereas an alternating current is going backwards and forwards, back and forwards. There's a range of values it could be, and we can transform the voltage from one value to another, and that's why it's so useful. So you can plug in your mobile phone charger and the voltage can be transformed to a lower level to allow your phone to be charged. If you use direct current, that can't happen. Okay, so that's the difference between an AC, an alternating current, where the current is going back and forth, and a DC current, it's only got one value only. The current is going one way around the circuit. Okay, so moving on swiftly, there are three types of wire in your plug or in your plastic casing that carries the electricity to the device. And I am going to need my colours this time. And I'm just wondering what I can't. Ah, here we are. I've got it here. So I don't know that I can get my colours on in the right way. Or have I got the right colours here? Okay, so you've got the live wire, and the live wire is the brown wire, and the live wire, which is coloured brown, takes electricity from the mains to the device. All right, in order to make the device work, takes electricity from mains to the device. Whereas the neutral wire, okay, the neutral wire is blue, and that will take the wire, the electricity, the electric current. It takes the electricity from the device back to mains. So it takes the electricity from the device back to mains. So actually, if you have a look at it in this ring main here, the brown is where the current goes in. And then there's a ring main here with kind of like lots of plugs on from all different appliances from around the house. So the houses have a ring main where all the plugs are connected into. It'll have a lighting circuit as well, but we're just looking at this ring main. So the current will come into this the ring main on the brown wire, and it'll go into the device through the live plug, and that will go into the device then, and then the current of the electricity will go out from the device through the neutral part of the plug, and then back out through the blue, right, and through here, and then out. Now, ideally, if you've got something plugged in there into the wall, let's just say it's a heater, and you've got, for example, 10 amps going in. So there'll be 10 amps going into the device through the live, and if it's working nicely and properly, then you'll have 10 amps that will come out through the neutral and back out. Because remember, it's not current that gets used up at all, it's the energy that gets used up, not the current. So that is when it's working perfectly. Now the earth wire is yellow and green. Both of those colours are needed. So this one will be the remaining one, the earth, the yellow and green. All right, and that acts as a safety feature. And the safety feature, if there is a fault, all right, and in normal circumstances there isn't, but if there is a fault, then electricity is taken down to ground through the earth. Okay, so this earth wire shouldn't have any current going in it at all. 10 amps goes in through the live, 10 amps comes out through the neutral, and there shouldn't be any current going through the earth when it's working normally. All right, and this symbol for the ground is that sort of symbol. So that means that if there is a fault, then the electricity will surge down to the ground. Instead of when you come to touch it going through you, it will go through the earth wire down to the ground so that you don't get that electric shock. So let's have a look in the case of this toaster. And this toaster has a fault. And you can see that the metal casing has been touched by the live wire, and it makes the live connected to the metal casing. It makes the metal casing live so that if you came to touch it, it would be set at 230 volts, so that when you come to touch it and you are firmly stood on the ground, there will be a potential difference of 230 volts through you, and you'll get an electric shock. So this is why the toaster is dangerous. There's a short circuit so that the metal casing is actually live. You don't want it to be that, because there's a short circuit, and there's a connection between the live and the metal casing, and that causes it to become live. So if you like, this is set at 230 volts, and that's the problem. So that when you come to touch it, you will get a massive electric shock and you might die. Okay, so what we need to do is attach an earth to the toaster, so that if there is a fault at all, then that metal casing is connected down to the ground so that any electricity created by a short circuit will flood down to the earth wire. In addition to having an earth wire connected to the toaster, we also put a fuse in. The fuse always goes in on the live. So when there's the short and all of that current goes and floods down to the, so the current's going in through here, and then it goes through the short here, and then literally it goes down through the metal casing and down the earth. That's what we call a short circuit. Now what it's going to do is, there's no resistance in that circuit at all, because the device is actually not in that circuit anymore because of the short, and it will blow the fuse in the live. So what fuses do is that if too much current flows, it breaks the circuit by melting the wire inside the fuse. We have to put it on the live. Like any switches, like any fuses, they all go on the live, so that the potential difference, if it does blow, is across the fuse. So in this particular situation, what will happen is that this will break here, and then all of a sudden you have got plus 230 volts here, and you've got 0 volts on the other side. And that means that now the metal casing is no longer live, and it's safe to be touched, and you won't get electric shock because you're set at 0 volts. The metal casing is now set at 0 volts because the fuse has broken. So everything else is set at 0 volts, and therefore you won't get an electric shock when you come to touch the metal casing. Okay. So for safety, we need 2 things: the earth wire and a fuse. But to make it really safe, the fuse must be placed within the live wire. All right, otherwise the metal casing will remain live. All right, and when it's broken, we want the metal casing to drop to 0 volts so that there won't be a potential difference through you. So fuses have ratings. So for example, 3 amp fuse, 5 amp fuse, 13 amp fuse that we can see here. And when we're using fuses, we have to kind of like look at how much power the appliance is using. For example, in this example here, there's a 2300 watt kettle, and it's plugged into the 230 volt mains. Sometimes the exam question might say 220 or 240 volts, but mainly it's 230 volts that we use. So we can use another equation that we use from circuit electricity that we did before. Power equals current times by voltage. And we can rearrange that from our PIV tree, okay, power on top, okay, PIV tree. We want to find out the current. So the current is power divided by voltage. If you're looking at it in terms of this equation, then the current is times by the voltage. So when you take it over onto the other side, it becomes divide. So power divided by voltage equals current. And you've got the same equation as if you did it by the triangle method. So we can work out, so current equals power divided by voltage, so 2300 divided by the voltage 230, and you can see straight away here it's going to be 10 amps. Now we can't use a 3 amp fuse here because in the normal working practice that kettle would say blow. Same with the 5 amp. So the next fuse up would be 13 amps. So we go with that, use a 13 amp fuse. They will give you a selection of fuses you can choose from, probably, in this sort of question. And there are other fuses other than 1, 3, 5 and 13. For example, 1 amp or a 10 amp fuse. But actually a 10 amp fuse, if we found one, wouldn't help here because at 10 amps we want the kettle to be working and not to kind of like fuse the circuit every time you switch it on. So the idea is with the fuses, they have a special rating so that if they go above that amount that they state on the fuse, then it's going to blow and melt the wire inside the casing and no longer be able to work the circuit because the circuit has been broken. So for example, a 13 amp fuse, if we have more than 13 amp in the circuit, for example 15 amp, then it will blow that fuse and it will no longer work and it will protect the circuit. Mainly things that need heating need higher rating fuses. But moving on, these are examples of something that doesn't need replacing, but can instead be resettable. So we call one of them is an MCB, a miniature circuit breaker, and another one is an RCCB, a residual current circuit breaker or a residual current circuit device. So the miniature circuit breaker, the beauty of both of these is that they are resettable. Unfortunately, with the fuses, once it's blown, and you'll have to go to a shop and you'll have to buy the special fuse to put it in the right location. So we do have to replace a fuse physically, whereas with circuit breakers, all we have to do is flick a switch and to be able to reset it. And that saves us money in the long term because we don't have to go and buy any new ones. But it also is very quick and easy because you can go straight to your fuse box, wherever your fuse box is in the house, and you can see which fuses are down compared to those that are up and reset them. So for example, if you've got a fault with your kettle, it might blow the fuse box, but it'll only blow one of the miniature circuit breakers. You go to the garage or utility room or in the kitchen, wherever you've got your fuse box, and you can reset them without having to replace it. And these work by electromagnetic switches, basically, so that if you have got wire, the current going in through the live and out through the neutral, then the live wire, the current through it will create an electromagnet, and that will pull the contacts open if the current is too strong. So at an ideal level, the contacts are closed, the circuit is closed, and the device is working normally. But when there's too much current flowing, those contacts can be pulled open because the electromagnet is very, very strong because you've got a lot of currents. Okay, and the contacts are here, so those will break open and the device will no longer work. A similar sort of system exists for a residual current circuit breaker, but the beauty of this is it's much more sensitive and it's much more accurate. With a fuse, you have to wait until the wire has melted, and this takes time. In the miniature circuit breaker, it is quicker acting, but the residual current circuit breaker is very, very sensitive, because what that's doing is it's got two electromagnets, basically one on the neutral and one on the live. And what it's doing is it's sensing a difference between the currents between the neutral and the live wires. So what we've got here is we've got a pivot system here. If the currents are different at all, then the electromagnets in the live part compared to the neutral part will, pivot this iron rocker, this lever system, and that will break the circuit because you've got this kind of button here which breaks the contacts if there's a difference in the currents, which is a difference in the strength of the electromagnet. Now, you don't need to go into too much detail about how they physically work, just to remember that our CCBs are much quicker acting and they are much more sensitive. All right, so that as soon as there is detected a difference between the currents in the live and the neutral, it will trigger that switch to come open. And we want this because it's much, much safer all of these things are safe, but the RCCBs are even safer because they are so sensitive. As soon as they detect any current going down through the earth, then they'll see that there's a difference in current between the live and the neutral, and flick a switch and switch the circuit off. Okay, so moving on, we are looking now at, I want to just touch on what we call micro generation of electricity. And that is all of the electricity that is generated by our houses. So some of us will have solar panels. Maybe if you live out in the countryside, you will have a wind turbine. So all of these things can contribute to the individual house's electricity and reduce your bills. Now, this is called microgeneration because all of that electricity that's generated from a small scale can be fed back into the national grid if you're not using it as a householder, and contribute to the national grid so that other people can draw upon it. So just looking at the top one, this is a typical wind turbine. And for typical wind speed, for example, of 5 meters per second, we can generate and get 1 kilowatt hour. So that's 1 unit of electricity per day. All right, doesn't look a lot, but clearly, if there's no wind, you're not going to generate any electricity. If there's more wind, you will generate electricity. But after a certain point, it gets really, really windy, they'll go into shutdown and not produce any electricity at all. All right, otherwise, the wind turbine will start taking off. Solar power, this one is solar. All right, and this is an example of how much electricity is being generated, or power is being generated during the course of the day. And if we look at one of these squares and how much it's worth, that would be 1 there, 6, and that would be 7 there. So one of these squares is 1 kilowatt hour long and 1 hour wide. So if I work out the area of that, that would be 1 kilowatt hour. So 1 unit is 1 square in this particular example. So if I count them all up, it's roughly around about 72 kilowatt hours per day. Now, that could be a sunny day, all right, where the sun is, kind of like rising 7 o'clock and increasing until about 7 o'clock at night. So that's probably not a winter's day. And it's looking like that there was a lot of sunlight, but if there is no sun or the cloud comes over, then this peak would drop down, and it would drop down to 0 at night time. But even when it's cloudy, you will still produce some electricity. If you are having to count squares, this is a skill. I wouldn't probably count this one because it's less than half, but I would count this one as 1 because it's more than half. And I'll leave you have a go and count up all of the squares that are underneath the curve, and that will give you the number of kilowatt hours used in a day. Now, you would think that that would be enough for the consumption of a household. 72 kilowatts and a 1 kilowatt together makes 73 kilowatt hours. That should be sufficient. The problem is, very often we need our electricity at night time when we come home from work, come home from school, it's starting to get dark. They don't produce any electricity when it's dark, and that's when we want to be making our meals, heating our houses, and lighting them. So actually, when it's not windy, we don't create any electricity. So in theory, it should be enough, but in practice, actually it doesn't produce the electricity when we need it. So maybe it goes back to the mains and you'll get a cost from that. You'll get some payback off your bills from that. And then maybe you then buy some back from the mains if you're not generating electricity in the house. So it's not so straightforward as you think, getting wind turbines and solar, but it does all help to your general bills. So looking at the last thing really, before looking at a couple of exam questions, let's have a look at a Sankey diagram. Now, this should be really drawn from, say, generation of electricity module, use of Sankey diagrams. And if we do one for the wind turbine, the kinetic energy is our input energy, and the electrical energy, is our useful output energy, because that's what we want out of a wind turbine. And the wasted energy is probably things like sound energy, and a safe bet is always going to be thermal energy or heat energy. Okay, and that would be our wasted. We tend to draw the wasted going down and the useful as going out along at the top. Whereas if we look at the solar cell, all right, and a solar cell is roughly, say, about 20% efficiency. All right, now with a solar cell, you've got radiation energy going onto a solar cell, or you can light energy. All right, and then the amount of energy that comes out as useful is electrical energy, because that's what we want out of it. And the wasted energy, again, is going to be thermal energy. Thermal energy. And we tend to use this one equation that you might have come from before. The percentage efficiency is the useful energy out divided by the total energy in. Remember, that's a divide sign, and then times by 100. So for example, if our efficiency is 20% and our total energy going in is say 5 kilowatts, all right, so that our useful energy out would be 20%, because whatever goes in, that would be 100%. Our useful coming out, useful output, would be the 20%. And then take 20% away from 100%, and that is your 80% that is wasted as thermal energy in the case of a solar cell. Okay, so if you've got 5 kilowatts going in, and that represents 100%, okay, then you to divide that by 100% and times it by 20% to work out what the useful energy out would be. So another way of looking at it is just 5 times by 20 over 100. Okay, so 5 times by divide by 5, so that would be 1 kilowatt. So there'll be 1 kilowatt coming out and 4 kilowatts being wasted, and add those two up. 1 kilowatt plus 4 kilowatts makes 5 kilowatts. So that's kind of like a little example of how we use that efficiency. But I also want to kind of like add in here that sometimes we have useful power output. Notice I've used power, or you can use the energy. So you might see it as useful energy out, but actually you can also use the useful power out divided by the total power in, because energy and power, the only difference is it's per second. So you can use it in kilowatts or in joules there. Okay, so let's just quickly have a look. The kilowatt is a convenient unit of power, and we use the kilowatt hour as the unit of energy. We've used these equations. Units used is power in kilowatts times time in hours. Okay, and the cost is the units used times by the cost per unit. If the cost per unit is given to you in pounds, you can write the cost in pounds. If it's given to you in pence, you write the cost in pence, and then you convert it. Data can be used from secondary sources. So we looked at our washing machine label, and we've looked at power ratings of domestic appliances. Our washing machine was a B rating. We've looked at the difference between AC and DC. We've looked at fuses, circuit breakers, and residual circuit breakers, and really that's preventing fires in the home by preventing too much current flowing in our circuit. And it's also kind of like mitigating against any short circuits that we have that could render the device live, so preventing shocks to you by incorporating, the earth wire, fuses, the circuit breakers. We've looked at the ring main and looked at the uses and the functions of the live, neutral and earth wires. And we've looked at the solar and wind energy equipment. Now, what I want to do though, is I'll look at the fuel cost savings and the payback time using the data by looking at a particular question. We've looked at, kind of in context, efficiency and energy outputs. All right. Now, I've got a couple of questions there that you can have a little go at. I want to actually jump onto this one. So have a go at both of them, and I'll go over them if we don't have time here on the last session where we can group together and you can ask questions. Now, here there's a table and it's showing how much energy is lost per minute. And it's showing it at 21 degrees, 22 degrees, and 23 degrees, if the house temperature is at that and set at that. For the loft, windows and walls, with and without insulation, without and with double glazing, without and with cavity wall insulation. So I want to do this because I kind of want to show you that actually we can use those equations that you have learned right at the beginning to look at the savings, not just the costs, but the savings. So if we put fiberglass installation in, then we are saving, if we have to, for example, the first question is for 23 degrees C. Householder spends money on installing the loft insulation and cavity wall insulation. And we've got to use those figures in the table to find the heat energy savings. Now, they're not asking for the cost, they're asking for the savings, but we can use exactly the same questions, same equations. So we see the fiberglass, we see the energy saved when we've installed the fiberglass. We see the energy saved with no insulation. So what we've got to do is take those two numbers away from one another. So 61,300 taken away 17,460 is 43,840. And that is the amount of energy saved by putting loft insulation in. Now we can do exactly the same for cavity wall insulation for a house of 23 degrees. So you've got no insulation and then you put insulation in, and then how much is it? How many joules is lost? So again, we take the two away from one another, 33,360 joules. So that's the energy saved. So how much in total? You'll have to add that all up together, okay, like that. All right, and that comes out as 77,200 joules per minute. Now, we want it though in terms of kilowatts. Now, the thing is to remember is 1 watt is equal to 1 joule per second. And they're wanting it in terms of kilowatts. So you know that 1 kilowatt is 1,000 watts. So if we take the number 77,200, that is joules per minute. So if you want it in watts, that is a joule per second. So you've got to divide that by 60 to get it in to per second. I'll put like that, per second. And then you divide it by 1,000 because you want it in kilowatts. And the answer then is 1.29. Okay. All right. So now we're looking at it that we are saving 1.15 kilowatt as a result of improved insulation. And this is why I want to show you this, because these are the units as they are given to you. But instead of looking at in terms of costs, I want you to look at it in terms of the savings. So instead of the, kind of like the cost that you're paying out, it's the cost, it's the amount of money that you are saving. So literally, just they all want to know how much money is calculated and saved each week. So the number of units used, right, work out, you've got this in kilowatts, so that's 1.15 kilowatts, times by 12 hours each day, 12. That is the number of units used, and that is in one day, 13.8. Okay, now that is the same as the units used here. So both of those are the same. So that would be 13.8 times by the cost per unit. They've given it to us here, times by 8p. Things have gone up since I've written this, and that would be equal to 110.4 pence. Notice I haven't converted it into pounds yet. I'll do that in a minute. Okay, so divide that by 100, £1 and 10p. But I don't put the p there, I just leave it in pounds. So that is for one day, but they want it for each week. So each week, 7 days times by £1.10 equals £7.70. Now, I know I haven't got a lot of space there. You will have more space. You could put the working out into that area. But sometimes it's quite nice to put it all where the equations are so that you are not going to transcribe it incorrectly. And then don't forget to put the answer on the answer line. WJC won't give you the mark. And then, see, clever thing here, using the weekly saving. So this is the weekly saving that you've worked out in pounds. Calculate how many weeks it would take to pay back the cost of installation of the insulation. All right. So what we're doing is we're trying to counteract the cost of paying for the insulation in the first place with when are we going to see the payback time, kind of like when are we going to see that over so that any savings we make is a direct reduction on our bills and not paying off what we had to pay to install it. So the total cost is 1,500 to install it. Divide it by £7.70 will be 194.8 weeks. Let's round that off to the nearest week, and 195 weeks, because if we did it 194, I wouldn't have paid it off then, but 195 weeks will have paid it off. So this is what we call the payback time. So you're using those equations to work out the savings and the payback time. Like for example, we've just had some solar panels fitted, and that say cost £5,000 for 10 solar panels. How long will it take? And we're saving, say, for example, £100 each month on our bills. How long would it take, to kind of like pay back the initial cost of installing it at £5,000? And so £5,000 divided by 100, you can see that it's going to cost, 50, it's going to take 50 months. That would be 50 months, wouldn't it, until we pay back the costs of installing the solar cells, which would be around about 5 years. Right, given an environmental benefit of reducing the heat energy, but if you needed to work it out, you would divide it by 12 months in a year. Given environmental benefit of reducing the heat loss energy from the homes, so you reduce the amount of carbon dioxide, i.e. reduce produced, i.e. you reduce the global warming. And I just wanted to kind of like highlight that in terms of using the equations, but slightly in a different context. I'll leave you have a go at this question, and I'll go over that at the very end. And I think we have now covered everything, and I'll draw this to a close for domestic electricity, and I look forward to hearing from you um, in the last session, and listening to the Waves one next session by James. And I'm going to say good night.